friends, welcome to the lecture. In this lecture we will continue our study of existence and uniqueness theorems for ordinary differential equation. So, if you recall, in previous lectures we have discussed the following first order nonlinear differential equation, that is dy by dt equal to f dy, yt naught equal to y naught, where f is a given function of t and y defined and continuous in some neighborhood of the point t naught comma y naught. And we have discussed the existence and uniqueness of this system 1 and 2 with the help of defining a iterated sequence of solutions. So, we can define a sequence of associated approximating solution as follows. So, we have taken yt naught equal to y naught and yj plus 1 t equal to y naught plus t2 t naught fs yjs ds, where j is running from 0 1 2 3 and so on. So, what we have done in previous class, that once we have defined this sequence of associated approximate solution, and then under the condition that f dy is satisfying the ellipsis condition in a rectangle R, we have shown that this sequence will converge to a solution, and that solution is continuous and satisfy the system 1 and 2. So, this we have already discussed in previous lecture, and we have discussed the following theorem, which is given as follows, that if f dy is a continuous function of t and y in a closed and bounded rectangle R and satisfy the ellipsis condition in terms of y in R, then the successive approximation yj, which we have defined earlier, converges uniformly on the interval j, and j is defined as t, all the t, such that modulus of t minus t naught is less than or equal to alpha, where alpha is defined as minimum of a and b by m, to a solution y of the differential equation 1 that satisfy the initial condition 2. So, this we have discussed. Now, based on this existence and uniqueness theorem, let us discuss certain example. So, first example is this, that given that y dash equal to t 1 plus y is the differential equation is given to us, and the initial condition is given y0 equal to minus 1, and we want to find out the solution satisfying the condition y0 equal to minus 1. But if you look at the domain where this y0 is equal to minus 1 is there, if you look at this 1 plus y is not defined in that particular region. So, here we cannot directly solve this particular equation by dividing by 1 plus y. It means generally if you look at this is a separable equation, and in a separable equation we can solve like y dash equal to t y plus 1, and if you want to solve this we simply write dy by y plus 1 equal to t dt, and we can solve like this is ln y plus 1 equal to this t square by 2 plus some constant. So, we can write y plus 1 equal to e to power t square by 2, and we can consider this constant as e to power c. So, you can write it like this, and we have y equal to c e to power t square by 2 minus 1. That is what we generally used to do, and then put y0 equal to minus 1, then you can see that here this c comes out to be 0, and you can say that our solution yt is coming out to be minus 1 identically. So, this is a constant solution given as minus 1. We can get the this solution in a different way also. If you look at this t, this is f dy is t into 1 plus y, and we can easily see that here if we define a domain like this, that R is a rectangle defined as all those a b in R2 such that modulus of t is less than or equal to a, and modulus of y plus 1 is less than or equal to b, and we define f dy as t into 1 plus y, then we can easily see that this f is continuous for all t, and we can also verify that this f dy satisfy the ellipsis condition, that is f t y1 minus f t y2 is equal to modulus of t y1 minus y2, and we can say that since modulus of t is less than or equal to a, we can say that this is less than or equal to a times modulus of y1 minus y2. So, it means that this f t y satisfy the Lipschitz condition in terms of y. So, it satisfies the Lipschitz condition. So, we can say that f is Lipschitz on rectangle R. So, by existence and uniqueness theorem, they exist a unique solution of the equation on modulus of t less than or equal to h, where h is minimum of a and b by m. And how this m we can define? M is the maximum of modulus of f t y, where t y belongs to this region R. So, we may observe that here, if you look at m is what? Maximum of this quantity, and you look at that t is bounded by a, and modulus of 1 plus y is bounded by b. So, we can say that this m is given by you can say that it is given by a b. A unique solution exists in the interval modulus t less than or equal to h, and we want to find out the unique solution. And we can observe here that y t equal to minus 1 is already a solution of this equation. If you look at that y t equal to minus 1, if you look at, then here y dash will be y dash t is equal to 0, because it is a constant solution. And if you look at it is given by t times, and y plus 1 is given as 1 minus 1, that is 0 here. So, it means that y t equal to minus 1 satisfies this equation, and we already know that it has a unique solution. So, it means that this is the solution which we are searching for. Okay. So, though we have this difficulty that 1 plus y may not be defined at one particular point of the domain, still with the help of existence and uniqueness theorem we can find out the solution, and in this case it is given as y t equal to minus 1. Now, coming on to example 2. Here we look at the following differential equation, so that the solution y t of the initial value problem, y dash equal to e to power minus t square plus y square, where y 0 equal to 1 is given as the initial condition, exists in this particular domain. T is greater than or equal to 0, less than or equal to root 2 upon 1 plus root 2 whole square. So, here actually we are looking only for the interval in which the solution exists. So, first of all we find out that solution exists, and then we try to find out in which interval this solution exists. So, here let us define the rectangle. So, here rectangle is defined in the sense that t is lying between 0 to this quantity root 2 upon 1 plus root 2 whole square, and y is defined as y minus y naught is 1 here. So, y modulus of y minus y naught less than or equal to b. So, this is the rectangle R we have defined, and now you utilize the existence and uniqueness theorem we have proved. So, first find out the maximum value of f t y. Here f t y is given as e to the power minus t square plus y square. So, we want to find out the maximum of this over the rectangle R. So, here maximum of t y belongs to R, and e to the power minus t square plus y square. So, we want to find out the maximum of this quantity. So, if you look at whatever t you will take, the maximum value of e to the power minus t square is 1, and value maximum value of y square, if you look at this we can write it y minus 1 less than or equal to b, greater than or equal to minus b. So, we can write y is less than or equal to 1 plus b, greater than or equal to 1 minus b. So, we can say that y is bounded by 1 plus b. So, we can say that y square is bounded by 1 plus b whole square. So, we can say that maximum of e to the power minus t square plus y square is going to be 1 plus b plus 1 whole square. So, once we have m, then we can utilize the existence and uniqueness theorem, and we say that solution exists in this interval where alpha is minimum of the h a given here like this. This is our a, and b by m, where m is defined like this. So, first of all you please observe here that here e to the power minus t square plus y square is a continuous function, and it is defined in this rectangle R, which is a closed rectangle. So, maximum exists. So, and we have already find out the maximum m, it is given as this, and it also satisfies the ellipsis conditions in this region. So, we can say that the solution exists, and we are just looking at the interval where the solution exists. So, here we want to find out the minimum of this quantity root 2 upon 1 plus root 2 whole square and b upon 1 plus b plus 1 whole square. So, here if you look at we have to find out this region for arbitrary b. So, we have to find out the maximum value of this. So, how to find out this maximum value? So, here we can easily observe that the largest h that we can achieve is the maximum value of the function b upon 1 plus b plus 1 whole square, and we can easily see that the maximum value is coming out to be root 2 upon 1 plus root 2 whole square, which is obtained at b is equal to root 2. So, how to find out the maximum value of this function? So, for that just look at you look at your g of b, you consider this as a new function of b. So, it is b 1 plus b plus 1 whole square, right, and we can get we consider this as a function of b, and to find out the maximum value of gb with respect to b, we just differentiate this g dash b. So, how to find out the g dash b? So, it is 1 plus b plus 1 whole square, and here we will get what 1 plus b plus 1 whole square minus b, and this is what differentiation of this, that is 2 b plus 1, right. So, if you simplify this, it is 1 plus b square plus 1 plus 2 b minus 2 b square minus 2 b. So, if you simplify, 2 b is cancelled out upon this quantity 1 plus b plus 1 whole square, and this is going to be 2 minus b square divided by this quantity. So, this implies that g dash b is going to be 0 when 2 minus b square is equal to 0. So, we can say that b is given as plus minus root 2. Now, we already assume that b is a positive quantity. So, we will not consider this minus of root 2. So, we simply say that b is equal to plus root 2 is a critical point of this, and we left it to you to show that this actually maximize the value of g of b with the maximum minima result. So, here we have seen that this gb can be extremized or can be maximized for b equal to root 2, and if you look at the value of this quantity when b equal to root 2 is given as root 2 upon 1 plus root 2 whole square, and it means that the solution of this problem exists for this quantity. This also is coming out to be the same root 2 upon 1 plus root 2 whole square. So, we can this say that solution exists in the set interval, that is t is greater than or equal to 0, less than or equal to this quantity root 2 upon 1 plus root 2 whole square. So, here we have shown that the solution yt of this initial value problem exists, and it is unique, and it is defined in this particular interval. And now moving on to next example, which is similar to this, and here we want to find out that show that the solution yt of the initial value problem y dash equal to e to the power y minus t whole square with the initial condition y0 equal to 1 exists in this set interval. So, it is again the similar problem, and if you look at the fty is given as e to the power y minus t whole square, and here since it is a continuous function in the closed rectangle which we are defined like this, t is lying between 0 to root 3 minus 1 upon 2 e to the power minus root 3 plus 1 by 2 whole square, comma y minus y naught is given as 1 less than or equal to b. So, in this rectangle which is a closed rectangle, here function fty is a continuous function. So, it is bounded, it will achieve the maximum value. So, we say that by existence and uniqueness theorem, this has a solution, and we want to find out the interval in which the solution exists. So, here we say that since fty is e to the power y minus t whole square, then we can easily see that it satisfies the ellipsis condition. Here we can simply say that since fty is equal to e to the power y minus t whole square, then we can easily check that double f by double y exists and it is continuous. So, you can simply say that e to power y minus t whole square and 2 of y minus t will be there. So, it is a continuous function and defined on this closed rectangle R. So, it will be bounded, and we have shown that if partial derivative exists and bounded, then f satisfy the ellipsis condition. As if you look at the previous case, in this example, when we look at f t y, here f t y is what? Here f t y is e to power t square plus y square, and we can easily check that it satisfy the ellipsis condition by finding out f t y 1 minus f t y 2, right. You just check that it is bounded by k times y 1 minus y 2. So, we can check that it is also satisfying the ellipsis condition. So, here we have shown that it satisfies the ellipsis condition by showing that this partial derivative exists and it is bounded by some constant k. So, it satisfies the all the condition of existence and uniqueness theorem. So, we can say that by existence and uniqueness theorem, the solution of this initial value problem exists, and in the exists in the interval which is given as 0 less than or equal to t less than or equal to minimum of the value a, which is given here, and b by m. Here b by m is given by e to power b plus 1 whole square. So, that you can easily check that how to find out this maximum value e to power b plus 1 square. If you look at here, so here your f t y is what? F t y is e to power y minus t whole square, and here your t is given as that t is greater than or equal to 0 to some a, where we have already defined what is a, and y minus 1 less than or equal to b. So, we have already seen that this implies that y is given by 1 plus b, 1 minus b. So, we can write that minus t, I can write minus t is greater than or equal to minus a less than or equal to 0. So, we can say that y minus t is written as y minus b minus a less than 1 plus b. So, we can say that y minus t whole square is bounded by 1 plus b whole square. So, it means that e to power y minus t whole square is less than or equal to e to power 1 plus b whole square. So, in this way we can find out the maximum value of f t y, and here we have the m is given as maximum of t y in rectangle R, e to power y minus t whole square. This is given as e to power b plus 1 whole square. So, we have to find out the interval in which the solution exists. So, for that we have to find out the maximum value of this quantity. So, again we can say that the clearly the largest edge that we can achieve is the maximum value of the function b upon e to power b plus 1 whole square. And how we can find out this maximum value, and we can say that the maximum value is given by the value this, and which is same as a, and which we can obtain by the b given as minus 1 plus root 3 upon 2. How we can achieve, if you look at this, so we need to find out the maximum of b upon e to power 1 plus b whole square, or you can write this as b into e to power minus 1 plus b whole square. So, we consider again this as g1b, some function of b. To find out the maximum value here, we look at g1 dash b as 0, and this implies that we have to look at this as e to power minus 1 plus b whole square plus b e to power minus 1 plus b whole square and into 2 of 1 plus b, and that is equal to 0. So, we can take out this e to power minus 1 plus b square out, and we can write this as e to power minus 1 plus b whole square, and within bracket it is what? 1 plus 2b plus 2b square. Is it okay? There is one minus sign here because of this. So, we have a minus sign here. So, it is all. So, here we have this minus and this is minus. So, here we can say that g1 dash b is equal to 0 provided that this quantity is 0. Now, what is this value? So, here we have this value 2b square plus 2b minus 1 equal to 0. So, it means that here b will be a 0 of this provided that 2b square plus 2b minus 1 is equal to 0. So, it is a quadratic equation and we can easily find out the root of this, and if you look at the root of this b is given as minus b, that is minus 2 plus minus 4 minus 4 into 2 into minus 1 divided by 2 into 2. So, it is minus 2 plus minus, it is 4 plus 8 divided by 4, and we can write minus 2 plus minus, it is 12 root 12. So, root 12 is given at 2 root 3 divided by 4. So, it is minus 1 plus minus root 3 upon 2. Now, here we have two values, minus 1 plus root 3 upon 2 and minus 1 minus root 3 upon 2, and since b satisfies this condition that y minus 1 less than or equal to b. So, it means that b has to be positive. So, if you consider this value, then this value is going to be a negative value of b. So, we have to take the value b which is given as minus 1 plus root 3 upon 2. I am leaving it to you to show that at this value this G1b achieve the maximum value. So, we say that in what we have shown here, that for this value b G1b extremize. Now, we can further check that it not only it extremize, it actually maximize the function G1b. So, that is what we wanted to show here. So, we have shown that the maximum value is achieved by b into power minus b plus 1 whole square. Now, b is given as root 3 minus 1 by 2, e to power minus b plus 1 is given by root 3 plus 1 by 2 whole square. So, here we have achieved the maximum value of b upon e plus e upon b upon e to power b plus 1 whole square as this value, and which is same as a. So, we can say that to summarize all this thing, we say that the by existence and uniqueness theorem, yt exists for this interval 0 less than or equal to t less than or equal to the a. Here a and b by m is coming out to be same. So, here we have proved that the solution yt of the initial value problem this exists, and it exists in this interval. If you look at so far we have discussed a few problems, and we have not in the previous problem and this problem we have not find out the solution. We are rather interested in finding the interval in which the solution exists. So, here we know that solution exists and it exists in this particular interval. Moving on, next we can write this, we can summarize this, that if in a region D, not necessarily a rectangle, the function f is satisfying ellipsis continuity in y, then given any point t0 y0 in D, we can construct a rectangle R lying entirely in domain D. So, it means that you initially start with a region R where this fty satisfies the ellipsis condition. So, in that region you can easily find out a rectangle containing the point t0 y0 such that that rectangle is purely contained in that region D, and there we can say that the hypothesis of theorem 1 are then true in R, and we can apply theorem 1 to find the existence of a solution yt of y dash equal to fty through the point t0 y0 on some interval about t0, and in fact it may happen a solution may exist on a larger interval than the one constructed in the proof of the theorem 1. So, it may happen that actually the solution exists in a larger interval, but your theorem is given only the small interval in which the solution exists. So, let us consider next example where we can point out this problem. So, if you look at this, consider the following initial value problem y dash equal to y square with y0 equal to 2. And this if you look at this is quite easy problem, it is y dash this is a separation variable problem. So, we can simply say that how we can solve this, we have simply y dash equal to y square and y0 is equal to 2. So, we can simply say that, so dy by y square is equal to dt, and you can simply solve this by minus 1 upon y t is equal to t plus c, and you can find out the value of c when y0 equal to 2, and we can simply say that the solution of this problem exists as yt equal to 2 upon 1 minus 2t. And if you look at this solution exists in this interval minus infinity less than t less than 1 by 2. And but if we use the existence and uniqueness theorem which we have given, we may define our rectangle R such that set of all ty such that modulus of t less than or equal to a, modulus of y minus y naught is 2 here, modulus of y minus 2 less than or equal to b. So here we can say that the maximum value of y square is going to be 2 plus b whole square. So m is given as maximum of ty in rectangle R y square, and that is given as 2 plus b whole square. And we can say that alpha, which is defined as minimum of a and b by m, is given as the maximum value of b by m. So here b by m, you can find out b upon 2 plus b whole square, and you can easily check that the solution. Let me do it. So here we have say GB as b upon b plus 2 whole square. I think this is the thing we have given. It is b upon 2 plus b whole square. So g dash b will be 0 provided we have b plus 2 whole square, and here we have b plus 2 whole square minus b to b plus 2. So if you simplify this, what you will get? You will get b plus 2, you can take it out. You have b plus 2 minus 2b, and you can easily see that this is g dash b equal to 0 provided that 2 minus b equal to 0. So we can get the maximum value at b equal to 2, and maximum value of GB is going to be 2 upon 2 plus 2 whole square means 16. So it is 1 by 8. So it means that the interval in which this solution exists is going to be alpha is 1 by 8. So here solution exists in modulus of t less than 1 by 8, but just now we have shown that the solution actually exists in this interval minus infinity to 1 by 2. But if you look at our theorem, this existence and uniqueness theorems assure the unique solution in this interval modulus t less than or equal to 1 by 8. It means that this existence and uniqueness theorem is a local existence theorem, means here solution is guaranteed only in a small neighborhood around the initial point. So we can simply say that theorem 1 is a local existence theorem and discuss the existence only in a small neighborhood of the initial point, that we may observe from the previous example. And the proof of this theorem required the ellipsis continuity of the nonlinear function even when we need only existence, because we have shown that this ellipsis continuity is required when we need a unique solution. So it means that regarding the existence of a solution 1, theorem 1 is not the only and best result. We may have existence of solution without uniqueness, and one such important result we can state as follows. Here we assume that suppose f is continuous on the rectangle R, and suppose f ty is bounded by this constant m for all points ty in R, and let alpha be the smaller of the positive numbers a and b by m, then there is a solution y of the differential equation 1 that satisfies the initial condition 2 existing on the interval t modulus of t minus t naught less than or equal to alpha. If you look at here we have not observed, here we have not required that fty satisfy the ellipsis continuity, and still the existence is guaranteed by this theorem. So we will look at more point based on this theorem 2 in next class. So here we stop, and we will continue next lecture. Thank you very much.